Um, I'm a physicist from the University of Paderborn, and I wanted actually to understand economics because I'm lacking equations which I can hold on to and which I can really calculate things and not have just a model and see what happens. So I will talk about economics, and if I understand it right, energy should turn out in the right way, in some way too, and so we'll see what happens. I'll talk about a model, a future model, about differential forms and line integrals, about accounting, about laws of economics, production and growth, and a summary. So I will start with a philosophical question. Why Why do we teach our children and students the knowledge of our past, even though they need the tools of tomorrow? So we do this because many things of today will be valid in the future. These are the V elements. But of course, many things of the future are today still unknown. These are the U elements. Okay, so and we can try to find examples for this future model. Well, science is typical. In science, all elements may be divided into two categories. They are always valid now and in the future. Those are the teaching facts. And then presently unknown, in the future known, these are the research results. But let's go more specific into different sciences. Let's go to economics. In economics, all elements may be divided into two categories. Ex ante, always known, like functions, for example, and U are the ex post terms, only known in the future, like income. We can file our income tax return only at the end of the year, not now. In physics, systems may be divided into two categories: conservative, always known, like the motion in conservative forces. Kepler's law of 1619 are still valid today, as space has no friction. And we have non-conservative motion, which is only known in the future, like turbulent motion in the weather. We have also mathematical examples of the future model. Two-dimensional calculus may be divided into two categories. We have exact differential forms with a known stem function, and we have not exact differential forms which do not have a stem function. Or we can use integrals. In calculus, integrals may be divided into two categories: Riemann integrals with paths independent and known, calculable, and we have Stokes integrals which are path dependent and the path is unknown. In statistics, all elements may be divided into two categories. They are known constraints with precise value, or they are unknown, they are probable, and precise value is only known in the future. And our data are real numbers. And real numbers may be divided into two categories: rational numbers. They are solutions of linear equations, and the solution is always known. And we have irrational numbers. They are solution of nonlinear equations, and they are very difficult to solve. Okay, now we can get more specific into economics, and I will look at possible mathematical tools for economics. We can use differential forms in macroeconomics. All the V are all ex ante terms must be written as exact differentials, and all ex post terms must be written as not exact differential because they are unknown and the other ones are known. Or we may write all ex ante terms written as Riemann integrals because they are known, and all ex post terms must be written as Stokes integrals, which are not known. Or we can use statistical theory in microeconomics. All ex ante terms must be written as constraints, as functions, and all ex post terms must be written as probability terms. Or we can use chaos theory and differential equations, and all ex ante terms must be written as linear differential equations, and all ex post terms must be written as nonlinear equations which are not solvable. Um, I will only talk about the first two parts, differential forms and linear integrals. It is obvious that statistical theory of microeconomics is done with statistics, and I think about chaos theory we'll hear somebody else at the end of this meeting. Let me shortly talk about differential forms and line integrals in case you have forgotten. In two-dimensional calculus, we have exact differentials f, df. F is the stem function, and df is formed by df dx, df y dy, and the mixed differential are equal. You can look this up here and calculate that if you want to. And not exact differential forms, delta m, have no stems function. They can be constructed, for example, by multiplying with an exact differential with x, and then we'll find the mixed differentials are not equal. We can do this. We can multiply x times df. This is df is up here, and df is x times df is 4x to the 4th, because one multiply with x. So this is here, and here we have x to the 5th. And if we now make the mixed differentials, we have here differentiating by y. This would be 7 times 4 is 28, and differentiating by x, and this is 35. 28 is not equal to 25 as a 35, so this is not exact. And these are very difficult differential forms. They are very difficult to handle. But there's hope. There is an integrating factor. We may reverse this equation and write df equals 1 over x dm. This means a not exact differential form may be transformed into an exact differential form by an integrating factor of 1 over x. So far about calculus of differential forms. I'll come back to this later. Let's look at integrals. A closed Riemann line integral of an exact differential is always 0. The integral from a to b is equal to the path from b to a, and the closed integral is 0. That is like going on a ring. You end where you started. Examples are mechanical energy in a conservative force, for example. And we have the u-terms, the unknown. A closed Stokes line integral of not exact differential form is never 0. The integral from a to b is not equal to the integral from b to a. The closed integral of dm is equals capital delta m, and that is not 0. Examples are magnetic fields or vortex fields, high or low in the weather. And these are actually spirals. Each term brings it up by delta m by 1, so closed integrals, Stokes integrals are spirals like magnetic fields, for example, or vortex fields, or the weather. Okay, now we have the line integrals, and now I come to accounting. I will first present the neoclassical flow model and give this example. A household works in industry earning 100 euro per day, spending 90 for food and goods, and the surplus is 10 euro per day. This is a very simple balance, and the neoclassical flow model tells us income flows from industry to households, and consumption costs flow back to industry. The surplus goes to the bank and back to industry for investment. So this is what I learned from many models, but this model unfortunately is wrong. Imagine industry pays 100 euro to the households and receives only 90 back from consumption costs. And the next day industry must borrow 10 euro from the bank to pay again 100 euro. That cannot be true. Industry will not go along with this. The neoclassical flow model is invalid. Unfortunately, yeah. This account is actually a Stokes integral. Integral pays the income of 100, and households pay, consumption costs and industry, and they are not equal. This is 100, this is 90. So this is a Stokes integral. And the balance is indeed not a ring. It is not that we have the zero balance, like the Italians say, the giro conto. This is not it's not a ring. It's a spiral. The spiral goes up by 10 euro every day. And if they mismanage, it goes down into deficit. So an unbalanced account is always an example for a Stokes line integral. It's a spiral, not a ring. So we can write this balance as dm equals ch minus yh income minus costs. And that is delta m, that's the surplus. So this is a new view on accounting. Now we want to do real accounting, and we go back now into economics to Luca Pacioli, who in 1494 wrote a book on mathematics, including double entry accounting. And looking at the same example again, he says, there is, of course, a monetary account with income and costs, but there's always a second account that matches this account. And these both add to zero. There is a productive account, because if the family earns 100 per day, they invest 100 euro in labor, in work. And if they spend 90 euros, they obtain 90 euros worth in goods. So these two accounts, the monetary account and the productive account, always must add to zero. And that's what they do. And the monetary account measures the productive account in euro. If we look at this productive account on labor or work and goods like food, they are originally measured in energy units. Labor is measured in megajoule and food in kilocalories. Everybody knows that. It stands on the foods. But Pacioli says in double entry accounting, the monetary account measures the productive account in euro. Okay, and since these accounts now I have shown are Stokes integrals, we can write this equation down. The monetary account plus the productive account add to zero. This is Pacioli in Stokes integrals. And now I come to the laws of economics. The laws of economics are based on Pacioli, which is valid now for more than 500 years. The monetary account measures the productive account in euro. And from this integral, we may derive the differential equation delta m equals dk minus delta r. How is that possible? Well, if we integrate, make the circular integral, then we have this over here, and integral minus dl, this is over here. And here we have the closed integral dk. This is the closed Riemann integral, and that is zero. So what we obtain from this integral is we obtain a differential equations which tells us that output depends on capital and labor input. And of course we have known that for many years. But this is the first time that we write this down as a differential equation. And these equations follow the future model. All not exact differential forms are written here as Stokes integrals. And here the same, all not exact differential forms, all ex post terms are written as not exact differential forms, and ex ante terms are written as exact differential forms. And now we have a second law here. We have the law delta m equals lambda df. This means the surplus, the output, is closely connected to a production function df, and this is the existence proof of the production function, because a not exact differential form may always be written as an exact differential form times an integrating factor. So this means there is a production function which always exists to any economic action where you have an output. The second law replaces the neoclassical solo equation y equals a times f of k and n. Instead, we have, well, delta m, let me say, this is income minus costs. So if you look at income here, this would say delta y equals lambda df. And you see Solo's equation is y equals a times f of k and n. This can only, if lambda is constant, you can integrate that, and then of course lambda is equal to a, and then this is true. But if lambda is not constant, the Solo equation is not correct. And lambda will turn out to be the standard of living, and the Solo model is actually made for economic growth, of change of standard of living, so lambda will change. So this Solo equation cannot be applied then, or at least only in restrictions. So this is the correct law that we have to use instead of the Solo model. Before I go on, I will look again at the Pacioli law. Pacioli said the monetary account is measures the productive account in monetary units. And since the productive account originally was measured in energy units, we could turn this around and say the productive account measures the monetary account in energy units. And we could turn money into energy, for example, by the oil price. And if we do this, we can write the same laws, okay, in monetary units, or we can write the same laws in energy units. I just changed the letters here to indicate that these are energy units. And if we look at these laws now here, we find these are the first and second law of thermodynamics. What we find is a structural identity of economics and thermodynamics. We find surplus is heat, capital is energy, wealth is enthalpy, production is work, mean capital means energy, a production function means entropy, the number is a number, the price per item corresponds to pressure, the volume or amounts to volume. The Lagrange function of economics corresponds to the free energy of thermodynamics, and the Le Chatelier function to the free enthalpy. So there's a one-to-one structural identity between economics and thermodynamics. And we can look at the GDP per capita for 125 biggest countries in the world and compare that to the energy consumption per capita, and we find there is a strict linearity between these two functions. So energy and capital are strictly corresponding here. Let me shortly say something about the production function entropy. Entropy replaces the Cobb-Douglas function of production. The Shannon entropy is ln x to the x, y to the y, instead of x to alpha, y to beta. The factors, the elasticities of alpha and beta are not anymore valid. It's now the function itself that leads to the elasticity. We do not need with entropy, we do not need elasticity here. And so the Shannon entropy x ln x plus y ln y replaces this function, and you see this function looks very similar, but it's much bigger, because the maximal production function, people thought the Cobb-Douglas function is the biggest one. It's not. The Shannon entropy is the biggest production function. It's much bigger than the Cobb-Douglas function. And entropy has a very important property. Entropy is a part of the production function of macroeconomics. Probability is a main part in microeconomics. And entropy, with being S equal L and P, is a link between macro and microeconomics. And you can go to microeconomics, but then you have to remember that S is the macro function S is also valid in microeconomics, and there it is called LNP. Let me shortly show how what entropy has to do with work. First, I will talk about entropy and disorder. A light breeze E, this is the first law here of thermodynamics, a light breeze in the park will easily empty a paper basket and generate disorder. That is entropy. The paper will never come back into the basket. But a janitor may come and work and sweep the paper together and put it back into the basket. Work reduces entropy. Work is ordering. And this is the function of the production function. In a big company or car company, there are lots of bolts and nuts and wheels and all things. And what do the workers do? They order these parts and reduce the entropy to make this car. And brain work people, they puzzle about this Gernot word. Well, it turns out to be ordering. And a doctor orders the body of his patient, and the teacher orders the brain of his students. And in addition, this term here shows that production costs depend on lambda, on the standard of living. Not only on the production function, but also on the lambda. And this means most people produce in China because there the standard of living is much lower. So this is very sensible. Now I will go into production and growth. I will use the closed integral of dq equals TdS. In motors, this is the Carnot process. And in economics, this is called the production process. In the Carnot motors, in the motor, we suck in cold air, and the exhaust is then limited again. And here is the same thing. We collect cheap, or buy cheap, sell expensive. Buy cheap, sell expensive. That is the same cycle as in the motor cycle with cold and hot. And let me show you this now on my example here. I will show this in an example of a trade between coal manufacturing in South Africa. Coal is distributed all over South Africa, and people now collect the coal. This is a TS diagram. This is the entropy. The coal is now brought to Cape Town, all over the country, and now it is collected. And now we have in Cape Town a big pile of cheap coal. And this is the first part. And then this is exported to Antwerp, to Europe, and there we have a big pile of expensive coal, because coal is much more expensive in Europe than it is in South Africa. And then the importer sells it to the customers. And before we finish this production cycle, I will look at the monetary cycle. The importer collects the money from his customers, and then he pays the exporter in South Africa. But of course he pays not everything, he keeps them for himself. And the exporter pays his worker and also keeps some for himself. And then the foreman can buy a car in Europe, and now the cycles are closed. The monetary cycle and the productive cycle are closed. And what happens now in this diagram, this is now the TS diagram, and the surplus that is produced, the profit, that is now divided to both sides. So both sides profit from this, and they start now over with the same process. But you see, they spiral up, they get richer, the earnings get higher and higher. So the production process is a Carnot process. And we can calculate economic growth by seeing how the profit is distributed. P is the percentage distributed to the lower side, to the poor side, and 1 minus P to the higher side. Okay, and there we get exponential growth if P is smaller than 0.5. We get linear growth for P equal 0.5, and we get stagnation if the lower parts gets too much money. This agrees and we can calculate, we can now compare this to trade. This is China-US trade, and we see this fits, the data fit very well to the calculations. And we see China triples their GDP in 20 years. US only has a 1.5 factor, but the actual values show that the the gap between rich and poor has grown from 24 to $41,000 per capita. So the machine of a motor gets always hotter and hotter and hotter. And the economic system gets always, the gap gets bigger and bigger and bigger. This is the result from this Carnot process. And this is the same result that has been found by Piketty for the last 2,000 years, that he says the lower side grows by 3% and the rich side by 4 to 6%, so the gap grows all the time. Let me now finish and ask, how does energy come into this? And we do this in thermodynamics by using the entropy, E equals P plus P times V. This is the entropy. Here we would have the wealth equals capital plus price times volume. And this is the price of energy times the volume of energy. And then the Q is the H minus VDP. This would then be the same corresponding term. The entropy stays the same. And in thermodynamics, we have to maximize the free Gibbs entropy. And this would be the same. We would have to maximize the Le Chatelier functions, W minus lambda F. That will lead to maximum. So this is the way I can propose that energy is inserted into economics. Because here in this model, I have not used physics. I have just used the laws of Pacioli. And this turned out to be very similar to thermodynamics. So I will not go into, I could repeat this again. Maybe I can just say, we cannot find y equals f of k, E, and L. This is impossible. We have wealth is capital times price times volume of energy. That is the way how we combine energy and money. Thank you very much.
Thank you very much for this very thoughtful talk, and I'm sure there are some questions. Yes? Can you speak loud?
Thanks for your talk. I have one question concerning the neoclassical circular flow model, because you claim that it's inconsistent.
Yes, it's a circle. It must be not a circle, but it must be a spiral. Because
nevertheless, you argued that it's inconsistent, although it's taught by 10,000s of professors.
Unfortunately, yeah. Yes.
It's at the core of each economic textbook.
Yes.
How come? So what's your social theory that nobody has noticed that it's inconsistent?
The lack of mass. You see, in physics, we start with mathematics of gradient, rotation, and divergence. Nobody knows that in economics. The gradient of wealth brings us the refugees from Africa here. This is a very important political function. And the rotation, the curl, is actually, every bank account is a curl. And it is like in the weather. And if you have a too strong deficit, you will have a very strong low, or in weather you would call a thunderstorm or even a cyclone. And if the Greek parliament, or if the Greek account gets too low, you have a real cyclone in the euro area, because this really disturbs everything in the European monetary system. So it is very important to know about these functions, curl and gradient and divergence. And nobody knows this in economics, because they think they don't need it because they don't work in space. But actually these functions are in physics they are vital, because you cannot do any theory in physics without these three terms: gradient, curl, and divergence. And this is part of this what I'm talking about here. It's the ideal. It's the ideal. Yes, it's the ideal. Yes, sure.
Because if you want to maximize the efficiency, you get no power, because it takes an infinite amount of time to exchange.
Yes, I know, I know. Carnot took.
Maximize the power. So, what is the equivalent of maximizing the power in economy?
I just argue that it's the same ideal process because Carnot, you see, this is the Stokes integral. You have no path, and Carnot defines this path as ideal path. But in reality, this is not valid. And the same is, of course, in economics. You have to look at the real path and see this is very close to this ideal path. But this is not only the ideal Carnot process, right? Yeah, your argument is right.
Yes. So
Can you introduce yourself, please?
yes, Antoine Monfort from Paris 13 University. I'm a macroeconomist and engineer. And I've already seen some talks, some work on similarities between energy, physics, and the economy. And I must say, I don't want to be disrespectful, but I do think that there is a really, really big problem in doing this kind of stuff when some physicists mostly go into economics without knowing much about it and try to find some similarities. An example, like what you what you base your work on is accounting identities. So that's okay. That's scientific. You cannot contest
Right.
accounting.
Yeah.
But the biggest thing about economics is to explain the relations that you can observe on accounts and find the causalities, the behavior of people. An example, accounting tells you that saving equal investment. That's accounting.
Yes.
There are multiple theories. Some say saving implies investment. You increase saving, you increase investment. Some say it's the other way around. And that's economics, because you
Yeah.
have to explain the
Yeah. No,
mechanism.
I say nothing. I just take the equations and take the solutions. And this is what I'm looking for in contrast to the models that are used. And you never know whether this is right or that is right. Sometimes they take the Keynes model and others say, no, I don't like it, I take another one. Would you ever in thermodynamics or in electricity say, I don't like this equation, I'll take another model? And even the iPhone is depending on the laws of the electric law of Maxwell, and you need these laws, and you can do lots of things based on this truth.
There are no laws. It's a social science. The laws
This is not true.
the functions are right at your first slide. You have the ex ante always true, always valid
Yes,
functions.
yes.
There is no such thing as. I mean,
Excuse me, if there is no law in economics, how can you perform a model in just don't follow the models? I mean, you just stop.
I'm worried
Which might be
because
a good idea, but
there are more physicists than economists here, and from the first question, I'm just afraid that you think that all economists are just doing nonsense and they are
No,
not.
no, I did not say this. This is not
It's not
true.
true. Even the neoclassical models, if you have a bank and interest, it can be stock flow consistent. And so the difference between theories is how you explain the behavior of people. So just, I'm
Yeah,
sorry, but
yeah.
really be cautious about this. And I have a physics question. As I said, I'm also an engineer, so when you talk about entropy, I know what it means. And when you say that work reduces entropy, if you put two leaves and you put them in a single basket, or you take wheels apart and the car and you build the whole car,
Yes.
you don't reduce entropy. Entropy is disorder at the micro structure.
No, it's a structure.
At the bigger,
You have
if I
thousands of
tidy my
parts.
room, I only create entropy because I move and I dissipate heat. I don't reduce
In a way, you can say it that way, but you order, and every housewife knows that ordering is work, and this is what happens here. So, but you misunderstand me. I argue that economists do not use math enough. I don't say that they don't do things right, but there are many things that are not right. Like, for example, the solo model is not really everything, because the second law is has much more power than a model of Solo, for example. The second law is valid not only in physics, it is valid worldwide. And so this is a thing you can trust on. But I don't say that the results you have found by thinking are all wrong. But I want to check this by equations. And I would see which one does right or which is not right. And so we can follow up with these laws all your economic steps and say, okay, this is right and this is not right. But I just want to create a basis on which you can check what you are doing. And you can extend this also to politics and also to social sciences, because that is the many particle systems which also are part of the thermodynamics. But I don't want to go that further.
Since we will keep entropy as low as possible, we will only take one more question. And please introduce yourself.
Okay, I'm Ugo Baldi from Italy, and thank you for this very interesting talk. A question: does thermodynamics apply to economics? Tell us something about social inequality. That is, how energy, intended as wealth, not energy, I'm sorry, entropy as wealth, is distributed in society.
Yes, I mean, the problem is you are starting a question for a specific problem. With the laws of thermodynamics, I can solve any problem in heat, anything. And I always go back to these equations. I can explain the furnace, or I can explain the metals and how the alloys work. There are very many different questions you can answer by that, just going back to these equations. And I'm very sure that you can go back to this problem too. I would have to think about it a little bit. I mean, I don't have all solutions at present at the moment. But this is a tool that works in science. Einstein says this is the most effective theory of all in physics. And I agree with that. And I think it is not applying only to physics, it also applies to many other fields.